Hi. So in this video we are going to discuss in some more detail the distinction between enantiomers and diastereoisomers. So recall the different categories of isomers we have been discussing. First of all, we have our isomer trees. Over here we have our isomers, and on the left we have constitutional isomers. Remember that these constitutional isomers have different connectivities, so they're actually fairly easy to distinguish from all the other stereoisomers. Now in stereoisomers here on the right, we have the same connectivity, but recall that the molecules are still not superimposable, like for any kind of isomer. We have basically different arrangement of the atoms in three-dimensional space. But now the key is that the stereoisomer class can be subdivided again into different types of stereoisomers. So first of all, we have enantiomers, as discussed, and these are non-superimposable mirror images. All right, now here the thing is that anything any two types of structures which are not mirror images and still not superimposable, still stereoisomers, they're classified as diastereoisomers. So as we said in class, diastereoisomers is kind of like just simply a collection basket for anything which are any two structures which are stereoisomers, but they're not mirror images, so they're not enantiomers. So that's what I want you to remember, that there are two subcategories of stereoisomers: the enantiomers, which are mirror images, and the diastereomers, which are pretty much everything else. An example for diastereomers would be cis and trans 2-butene, which we have also seen in lecture already. So here's cis-butene, trans-butene, and these two structures clearly are stereoisomers, but they're not mirror images. And this is why they are classified as diastereomers. Sometimes the formal name actually is not diastereomer, it's called diastereoisomer, but I will accept diastereomer. Okay, so remember that enantiomers, of course, have identical physical properties, except for optical rotation. But now for diastereomers, they're different. They're not mirror images of each other, and so they have different physical properties like melting point, boiling point, etc. Right? So now finally, I just want to show you one example what happens if you have multiple stereo centers in a compound. And things can get a little complicated. So let's look at the cyclohexane with three different substituents. And that this is it. We have a chlorine substituent, a methyl, and an OH substituent. And the first isomer here, the first stereoisomer I drew, has all three substituents pointing up. So all of the substituents are cis to each other on the same side of the molecule. Right? So we can now do the Kahn-Ingold-Prelog. We can apply the Kahn-Ingold-Prelog rules to all three stereocenters and assign them as either R or S. And so in this case, this compound would be R in the 1 position, R in the 2 position, and S in the 3 position. So we would call it 1R, 2R, 3S. Now we can, of course, draw the enantiomer of this compound, and we do that by flipping all the stereocenters, like changing all the wedges to dashes. So we would get this compound here, which is classified as 1S, 2S, 3R. Okay, see, all the stereocenters flip the configuration from R to S or vice versa. Now these two things are enantiomers, so we put them in a green box. But now we can draw another diastereomer of the original compound by flipping just one of the stereocenters. So here the configuration would be 1R, 2R, 3R. Before it was 3S, right? And so these two compounds, this is not what we just drew is not an enantiomer of anything we had before. So it's a diastereomer, but you can also see that by looking at whether the substituents are cis or trans. So here you see now the OH and the methyl groups, the alcohol and the methyl group, they are cis, and then the methyl group and the chlorine are trans. Okay, but now we can draw of course, the enantiomer of this compound, again, by flipping all the stereocenters, we get the 1S, 2S, 3S, and again, these are enantiomers now. And so we can keep going with this method. Right, I'm going to draw all the other Diastereomers. So here the 1R2S, 3S, and then the enantiomer. And finally the last possible one, which is the 1R2S, 3R. Right? And again, it's an enantiomer. And that's it. So you see we have here, with just 3 stereocenters, there are actually 8 possible stereoisomers. Right? And 4 pairs of these, they're all in the green boxes, they're enantiomers. And remember, each compound, again, can only have 1 enantiomer, only 1 mirror image. But then all the other pairs, there's many, many other pairs here, these are all diastereomers. Okay? So that's it. Now, just want to look at one more example here. Cholesterol, a typical, that's a compound, right, in our cell membranes. They cause blockage. Causes blockage of the arteries when you get old. So, but let's look at cholesterol. And the general rule is that if you have n stereocenters in a compound, you can have a maximum number of 2 to the n possible stereoisomers. Okay. So what does this mean for cholesterol? What's the maximum number of stereoisomers for cholesterol? Well, here's the compound. That's what it is. That's the actual stereoisomer which is present in nature, and it has, believe it or not, no less than 8 stereocenters in total. And this means that there are 256 stereoisomers possible for cholesterol. So 2 to the 8. Okay, so practice recognizing these stereocenters and figuring out how many stereoisomers there are and whether stereoisomers are enantiomers or diastereomers with Skill Builder 5.6. Thank you for watching.